And what's delta? Yeah, -1 in this case. All right, and so let's put that into the rate equation. RA, you go to K, and then CA is this big expression, FA naught, times 1 minus X divided by the initial volumetric flow rate, 1 plus epsilon times conversion, and then CB, FA naught times, what goes here, 1 or 2? 2. Why? Is that because of stoichiometry? In a roundabout way. It's because, yeah, that's big theta, right? So it's because the feed is stoichiometric. Minus this 2 is from stoichiometry. 2 times X. Same thing in the denominator, excuse me. Because volume is changing the same for both concentrations, right? Yeah. Yeah, so it is from stoichiometry, but I don't have to give you a stoichiometric feed.
What would happen if it wasn't a stoichiometric feed?
So that is big theta V, which is equal to FB naught over FA naught. All right, so you can rearrange this, and you get 2 times K. What is FA naught over V naught?
CA naught.
CA naught, the initial concentration. So is this always true for this problem? Or only at certain conditions?
For this problem? 0.41.
Only when X is less than that critical conversion. Because remember that we didn't actually take into account that we condensed anything when we did everything that we just did. This is just what we would get if this was a purely gas-phase system. So it's only true when it is a purely gas-phase system. It's only a purely gas-phase system when we're less than 40% conversion. So now we get to do it again. Okay, so when so the volumetric flow rate at any point is equal to this inlet volumetric flow rate and then the ratio of the two feeds. And this is the same thing. This is because the concentration in the gas is equal to the inlet concentration of all gas-phase species. Why is that true? How do we get CTO again? How do we do that last problem? Yeah, ideal gas law, right? So if the temperature is not changing and the pressure is not changing, then the total concentration of gas-phase species isn't changing. So this is true because we're at constant temperature and pressure. And we have an expression for Ft, sorry I had to erase it, from our stoichiometric table when we had condensation, right? So that's what we put for Ft earlier, and of course now we have to divide by Ft naught, which is 3 times the initial flow rate of A. So we get both of these the stoichiometric table that we wrote out a little while ago. So that's just the ratio of the flow rate. So to go back to our flow rate at any point, it's the initial flow rate, and then we'll just simplify that. 3 minus 2 times x, 3 times 1 minus y d at vapor-liquid equilibrium. Okay, so remember that's the first thing that we needed, right? Because now we want to write concentration, and that's FA over V. So before, the volumetric flow rate, when all we had to do was worry about the gas phase, the volumetric flow rate only depended upon epsilon. Now it depends on epsilon, but it also depends on the partial pressure of D in the gas, because that's now fixed at the vapor-liquid equilibrium amount. All right, so the rest of this is mostly just math. Divided by this mess. And then we do it again for B. The volumetric flow rate term is the same, this one again. Now the only difference is what we put here. FA naught 2 minus 2x. And so I'm just going to skip to the simplified form. I don't want you guys to have gaps in your notes, so I'll put it up again. Okay, so let's pause, because this is algebra, and you guys know how to do algebra. All right, well. What's different about this compared to the one that we just did? Now that things are condensing, the strategy of solving the problem has shifted just a small amount. It just comes back to here, okay? This is the equation that you can't forget when now you have to deal with phase change. This is the equation that you write down in order to get the volumetric flow rate in terms of stuff we know, or things in terms of conversion, which we know all of this in terms of conversion already. This is how we get the volumetric flow rate when there's condensation taking place. Okay? So if you start here and just start solving things, we get these from our stoichiometric table. The rest of this is algebra. Any questions about that? Yeah.
What happens when x is the critical conversion?
It works either way.
Okay.
By the same reason that, it was pointed out earlier that it is a continuous function, so is the rate. It's also a continuous function. All right, so to complete the algebraic exercise, I'll put the final rate equation on the board. But remember that this is only true when so we have both. I mean, don't forget that this is only true for this part of the reactor, right? You have both. Okay, and the problem statement asks not just for rates, but also total flows. So we'll say when X is less than XC, then the flow rate of D in the gas, well, let's do it this way. The flow rate of D is equal to the flow rate of D in the gas, right? There's no other flow of D because it's all still in the gas. And that is just equal to FAO times X. That's just from the stoichiometric table. When X is greater than the critical, now I have two flow rates leaving my reactor of D. I have a liquid and a gas flow rate. The gas flow rate is now no longer FAO times X, but instead YD at vapor liquid equilibrium times the total flow. The liquid flow rate, now let's solve it a little bit differently. Let's say this is the gas, just so we can finish that one, and then we'll talk about the liquid. So the gas flow rate is the molar fraction of D times the total flow rate. Remember that I have the total flow rate in terms of conversion already. That was in my stoichiometric table. So now I'm just plugging it in. What about the liquid?
Just FA naught X minus that,
Yeah, why?
because the total amount of D is still the same.
The total amount of D is still the same whether or not you're condensing it or not. The total amount of D is simply a function of conversion. So the total amount of D is not changing. So if the total amount of D is FA naught X, then the liquid is just the total amount minus that mess. Okay. So that's a tricky one, right? So far things have been pretty straightforward in the class, I think anyway. We've had to deal with volumetric changes in volumetric flow rate, but that's not that hard to deal with. That's just looking at the stoichiometry and recognizing that A goes to 2B is going to make things have to flow faster at constant pressure. This is the first time that, to me, the course gets kind of tricky because we have to think back to vapor-liquid equilibrium. We're going to keep that nice and simple, Raoult's law, right? If it's ever not Raoult's law, you'll be given the activity coefficient. Okay? You're not expected to do anything to solve activity coefficients. So if you have two products condensing, you'll be given their activity coefficients. But a lot of the times it's going to be a single product condensing. So Raoult's law works just fine. And now the big trick, right, is to remember how do I solve for the volumetric flow rate when I have a species condensing. And all I have to do there is keep in mind that the total concentration of the gas-phase species is constant as I go down the reactor bed because I'm at constant temperature and constant pressure. Any questions? Okay, we're done early today. This, you mean? I hope. I hope, right? That's just good geometry. It is, but one thing I don't like is that suddenly the floor rate changes medium, right? The FD is now which is massive, and even the note code is too consistent on the handle it and everything. So, I mean, just be consistent if you're working through the problem, and that way you won't forget. So, you know, if you're gonna put FD, you need to know what that means. Total flow rate, pushing right after, liquid flow rate, I'm gonna go home.
No, I gotta see.
JR, man.
Get what's up? Thank you. Wait, whose camera is that? Josh's. Wait 1 second, take this.